Hi, I'm Dr. Tania Hazra. Welcome to my STEM Day talk. This year, we're doing STEM and Psych Day virtually, and this video is on applied mathematics. Since my research area is mathematical biology, I'll introduce a bit of that branch in this video. Okay, so let's start. I'll start with counting, and at a very early age we start counting and then um, adding subtracting multiplication division, all those things. But when you come to schools or universities, we don't deal with those basic operations anymore. It's a little bit different. In the very first semester you take calculus, um, next set theory, and so on. So broadly speaking, mathematics is divided into two areas, um, quote unquote division, pure math and applied math. And if you go for pure math courses, you will see algebra, not only with numbers, you have theory based algebra as well, real analysis. So I can talk about a little bit on real analysis. When we start counting, it's just one, two, three, four, and so on. Then if there is nothing, we call the answer is zero, right? And for negative integers, we include -1, -2, and the negative numbers. After that, fraction, like a number a divided by b, provided the denominator is not equal to zero. Also, the irrationals, which cannot be expressed as a fraction. So all these numbers are called real numbers, and the analysis is depending on this real number system. Next one, complex analysis. So if you're solving one equation like x squared plus 1 equals to 0, and you get square root of -1, you get the first imaginary number as I. So with that extension, complex analysis starts. Later on, topology, geometry, the properties of geometric objects, logic, and number theory. So I can go on with more branches, but let's look at the applied math segments as well. So mathematical economics, physics, chemistry, financial math, mathematical biology, also computational math, optimization. So these are all fields where math is used. So math is a very strong tool to analyze the data, the structure, to predict something, and often it involves coding with different type of languages like Fortran, C++, MATLAB, RStudio. So not only pure and applied separately, they do intersect. Um, think about, combinatorics. Also, I can go a little farther. Pure applied math along with statistics. There are some region where pure math meets statistics, like measure theory. Also, applied math intersects a lot with statistics, like whenever we do data analysis or predicting some model. Think about this COVID-19 data. We come up with the constant sometimes with the statistics, statistical model, and also mathematical model. So it's hard to differentiate between which branch is used more. Rather, a lot of time combination of different branches. So let's talk about math in daily life. Think about swiping a card in a grocery store. So what happens actually, the data is encrypted while swiping your card. And 100 years back, when we were doing number theory, nobody knew the usage of those kind of theories like factoring and then finding prime numbers and so on. But these days, number theory is strongly used in cybersecurity and this code breaking, etc. A little more. I think I can talk about a little bit of Google search. Um, Wherever you are, you can Google university and see what happens. I got this page. So Misericordia University popped up because I'm very close. I live very close to Misericordia University and a few more schools near me. How does it find uh, Misericordia University? So depending on my clicks and my interest, geographic location, it filters my search. Not only that, if I go further, let's add one more character to it, Misericordia University. So, why is it coming up? Because this is probably most used, most searched, and rank wise at the top of the search. That's why it's popping up at first. So, what's going behind the scene? It's actually a matrix. It depends on what kind of search we are doing. So university, and then if you go for subject, scholarship, or if you're interested in different type of minors, as I mean, when you add some characters, it just increases the dimension of the matrix and it filters according to your choice of words. So the keywords are really important for when you are searching. So as I was saying, it's behind the scene and you can see Google metrics. And often it's million by million size. We cover linear algebra in second year of bachelor's, and it's just the extension of this matrices. Uh, there are eigenvalue, eigenvector, and adjoint, this kind of matrix or operation, but at higher level. So I mentioned linear algebra and some analysis. So, what do you think? It's pure math or applied math? Well, it's really hard to differentiate, you know? There are many topics which were unknown and which were not quote unquote useful 100 years back, just like the number theory. But today, those are useful. So, let me talk about how I was attracted to applied math. Originally, I'm from pure math background. I completed my master's in pure math, and I had all these sort of pure math topics like algebra, analysis, real analysis, complex analysis, topology, and so on. So when I uh, thought about doing some research, I started talking to some professors in my department, and I recommend whenever you're interested in some topic, talk to your professor. With his or her recommendation, maybe you can find some interesting topic. So, what happened? One professor gave me a problem from partial differential equation, and I had no clue how to do it. But he guided me a little bit. So I did some coding on a matrix and found this heat equation. So you know what? It was really a cool thing to observe the heat equation, and as the time goes from 0 to 10, for example, the change in surface, it's quite visible, and I was able to code it. So that was really exciting to me. For the first time, I got one application of linear algebra to numerical analysis, and it was really fascinating to me. So later on, when I started doing research, I chose mathematical biology. So from applied math to mathematical biology, I'm entering slowly. I work on proteins. Definitely, I have a mathematical model, and my goal is finding solvation free energy um, for a protein. So what is done with the solvation free energy? It is used in protein folding, protein ligand binding, DNA transcription, DNA translation, also RNA transcription and translation, drug discovery. So there are plenty of usage of this solvation-free energy. So let's go a little behind. How do I collect data before doing even any kind of mathematical modeling? So first, in the labs, not as mathematician, some experts do collect protein crystal, and the crystal is placed in the X-ray beam, and X-rays are diffracted by the electron clouds around atoms, and it identifies the bonds, and the atomic structure can be deducted from that data. It's a long process, and some experts do that. And finally, when they collect the atomic data, that data is stored in protein data bank, and that protein data bank is accessible to everybody. It's the website rcsb.org. And if you go there, you'll see lots of cool pictures with the proteins. And recently, with the COVID-19, there are tons of data. So you can see different types of structures, their amino acid, all types of information. Next, what I do with this data, I go for some suitable protein. I mean, it could be COVID-19 related, can be some infection related, like this 2NVH, one of my proteins took for my research. I download this data, PDB format, protein data bank format. And what the data gives me, atom center. So those are like spherical balls. And it has the center XYZ, also the radius, and partial charge. So total charge and partial charge distributed to every single atom. That information I get from that data. So when I do math modeling, it's not like this rainbow cluster to me. Rather, it looks like this. So it gives me the atom. I am showing you 1 to 10, but originally it's like 500 to 50,000. So very large protein. They label the atoms 1, 2, and so on. It depends from system to system. So nitrogen, hydrogen, calcium, what kind of atom it is, and it specifies the chain. Also tells you the center of the atom, charge, and radius. So I pick these 5 information and insert those information in my Paschen-Boltzmann equation, which is a partial differential equation. So this this equation may look crazy, but it handles a few dielectric constants, and the equation is solved for this electrostatic potential. And there are a few constants like Debye-Hackel parameter, and this EC is fundamental charge, KB is Boltzmann constant, and T is temperature, room temperature. So I can keep going, but the whole point is, what do I get using this, solving this equation? So I have electrostatic potential that helps me finding solvation-free energy. That solvation-free energy is used to understand the protein's behavior, and later on for protein folding, stable or coiled state, etc. So I don't know much on that segment, but I provide like who does mathematical biology provide that salvation-free energy to people who need those values, and they can analyze later on. So not going to into detail, but I can say, well, this equation, when it was modeled, it used physics, Coulomb's law, chemistry, of course, with the bonding hydrogen, carbon, oxygen, etc., from the electron clouds, and biology, of course, and mathematics. Now, in mathematics, it's really hard to give you the entire list, but I'm giving you a few as much as I can, like linear algebra, differential equation, real analysis. And using real analysis was really fascinating here. When we handle every single atom, we cannot take the whole domain. It will be really costly to use the entire space provided by the methods, So we had to create tiny boxes around those atoms. And those domain creation uses that real analysis. And even more, when I created my super Gaussian dielectric model, we had to do one effective dielectric constant analysis, and that used one technique, um, area under the curve. So definitely at higher dimension in 3D, but it's there. Application of calculus. Next one, numeric analysis, of course, with the coding, topology. So whenever we get the protein, we need to separate the molecular region and the solvent region, and to differentiate between molecular surface and the solvent region, we need a tightly packed surface, molecular surface, and to generate that, we need topology. Next, definitely scientific coding. It's a bunch of packages, and they compiled together to get the result. So, and once we get the salvation free energy from many atoms, we observe the behavior, which component affects what the most. It depends from experiment to experiment. So the list goes on. Next, a few more. Mathematical biology is not definitely limited to this protein usage. You can use mathematical modeling to immunology, tumor growth, infectious disease, epidemic, and we see the COVID-19 growth, the total cases, new cases, total deaths, etc. So different type of analysis can be done. Data analysis, of course, vaccination, modeling blood cell production, also blood pressure oscillation. Well, I hope you got some idea about applied math. If you have any question, please send me an email at thhazra@misericordia.edu. And I may not know all the topics, but I love to explore and get back to you. So that's all for today. Thank you.